So I'll introduce our speaker. Our speaker today is Yonggang Hu, who's an IBM Distinguished Engineer with a focus on applied AI, high-performance computing, and quantum computing. Yonggang is currently focused on emerging AI and computing technologies to address needs in core business workflows. He's responsible for the roadmap and strategy of IBM high-performance middleware and AI runtime. Over the past 20 years, Yonggang has architected and delivered fundamental technologies that power the largest high-performance analytics and AI productions at 15 of the top 20 banks in the world. Before joining IBM, Yonggang was vice president at JPMorgan Chase, focusing on computational analytics and application infrastructure. Yonggang holds an MS in computer science from Peking University and an MBA from Cornell University. The talk today, Yonggang will speak about the current state of big computing and big data technology being used at banks. He'll discuss the business drivers and computational models that drive the computing demands. He'll further share the potential and impact of some emerging technologies, such as cloud, AI, and quantum computing. Thank you very much, Yonggang.
Yeah, thank you. Thank you, Lisa, for the invitation. Very glad to be here to share some perspective. I actually have some chart. Maybe I can share my screen.
Are you able to just share your screen using the share screen?
Let me try. Can you hear me okay?
Yes, perfect.
Yeah, I just made you co-host. You should be able to share now.
Okay. Can you see my screen?
Yeah.
Yeah.
Okay. Okay, let's get started. So this is something I want to talk about today. This is about computation, since we all computer science major. And then I also want to talk about the financial service as well. Within the financial services, there are different type of calculation. Roughly, there are three types. There's a forecast, essentially try to predict the future. There's a simulation, and also optimization. From a computation perspective, currently high-performance computing is being used at the bank all over the world. And in future, quantum computing can also contribute. At the outer circle, there are a bunch of AI technology currently definitely changing the landscape of forecast, simulation, and optimization. And then there's a bunch of different financial service domain, which can be benefited by those computational technology and also AI technology. This is a very big domain, right? We only have 1 hour, and here's my plan for the hour. I will start with some introduction on HPC, and then I will talk about the specific application in financial services. Essentially to answer why all the big bank, hedge fund will require HPC capability. And then I will talk about AI, how AI changing the landscape. I will give a couple of examples. And the very last, I will touch upon quantum computing in future. And just feel free to interrupt me if you have any question. And I will share some picture. I will maybe also share a little bit of code, some formula, and interrupt me if you have any question. Is that okay for this agenda? Okay. Let's look at what is HPC. HPC, probably in your mind, it's about a lot of big machines, big errands, maybe doing a lot of scientific stuff, maybe in the movie. It is true, HPC can be very high-end. IBM built a supercomputer for Department of Energy at Oak Ridge National Lab, and this is one of the fastest supercomputer in the world. It was #1 in the world for a few years, and right now there's another computer in Japan is faster than this Summit supercomputer built by IBM. On the right-hand side, if you can see my cursor, is the quantum computer that IBM have built. And quantum computing have great potential to give further speed up for a lot of very difficult computational problem. So this is a pop quiz. We want to know, maybe I want to ask you, what do you think of the price of a Tesla GPU? Do you know anybody have an answer for that? Tesla is not the latest version. The latest version is A100. And here, the picture I show here is V100. Just to make a quick guess, how much it costs? Any idea? So this is a price of a car, a Nissan car. That car can last for many years, but this GPU could be outdated maybe in a couple of years. And the next one is IBM built this GPU machine, and the price tag for that one is 80K. 80K, I have Audi, but I don't have this version. I have A4. This is maybe my dream car. One day I will have A8. The next machine is NVIDIA DGX machine. Over there, it has a 32 GPU. And this is the price of a Lamborghini. And the last one, the Summit supercomputer that IBM have built, have this price tag. This is in the similar range of Formula One racing car. Formula One racing team maybe have a budget of $200 million to $500 million to build a fuel car. And the high-end supercomputer is in the same price range. So this is give you an idea of the cost doing compute. There is a significant price tag for HPC. You may ask why HPC relevant to us, why it's relevant to daily life. And here are a few examples. There is a HPC behind to create a potato chips. It is use computational fluid dynamics to calculate the airflow so that the chips will not fly around on the production assembly line, production pipeline, and also use the structural mechanics to study whether the chip can sustain the shape during the transportation. Similarly, for the production for making chocolate, the computational fluid dynamics is used to measure the cooling and the flow of chocolate to prevent the blockage for the production. And there are many examples. Chemical engineering, for hairspray is not the best example. this chemical engineering is super important for material discovery, for drug discovery. They all use HPC, and in future will have potential to use quantum computing. For agriculture, building the machine for crash test, for soil modeling, for structural dynamics. When we talk about building cars, the same thing. Need to measure the airflow to have computational fluid dynamics, and also crash test. When you have see the animation movie, and all the animation rendering actually all use HPC behind the scene to create all those interesting, fantastic movie. Chip design is another big area using HPC. And for the commercial domain, for example, SAS is one of the leading software for analytics, predictive analytics. Over there, I actually bundle IBM HPC technology to run all the calculation. So those are the examples that affect the daily life. And then AI also also drive a significant computational demand. And this is a chart from OpenAI, essentially showing the trend of computing demand driven by all the AI models from early days AlexNet to at the 2019 AlphaZero. And here is a log scale. This is not linear. Essentially, AI training compute demand increase with 3.5 months doubling since 2013. As we all know, the Moore's law is 18 months doubling. However, the computational demand from AI is doubling every 3.5 months. And then for the past couple of years, this language model also generates a significant better output than the previous language model. On the other hand, those latest language model also have a significant demand on computation. So essentially, modern days, if you want to do AI training, if you want to generate a good result, you will essentially need three things. One is big data. You need to have a lot of data to do the training. In this specific case, it's a GPT-3. It's one of the model from OpenAI. It uses 500 billion tokens data set to do the training. And then the AI researcher designed this large model and also training process. It uses self-supervised training. It's very hard to label such a big data. That's why this self-supervised training is extremely important. Essentially, you have a large paragraph, for example, it blocks a certain area, and then train the machine to guess what's the area, the text being blocked. And the model itself is very big. For GPT-3, it has 175 billion parameters. To do the training for such a large model against such a large data set, you need a supercomputer-like capability to do the training. And this is one example from Microsoft. it built an AI environment with 285,000 cores with a 10K GPU. By the way, the Summit supercomputer that IBM built over there, it has 22,000 GPUs. So you have to use HPC to do this type of training. If you don't have a HPC type of environment, it will take 355 years to train on one GPU card. And as I showed earlier, and this one GPU costs roughly $10,000. And the total cost for the training is around $4.6 million. And the model just keep growing and bigger. Last couple of weeks, there was a new model from China called Wudao. And that new model have 1.7 trillion parameters. Of course, that was trained on supercomputer. So let's look into the banking. What exactly the business driver for compute? Here is an article published more than 10 years ago, talking about JPMorgan looking for infinite capacity in our computer system. And this is also a starting point. I have been working with all the different banks to create the next generation computing environment for banking workload. Right? Why they need infinite capacity? To understand, we have to look at some example. This is an example, a very simple example of a financial instrument called a derivative, and this is a call option. Maybe just raise a hand. Do I need to explain the option or call option? If you are okay. Okay, then I can provide a quick explanation. So call option have many types, and the call option is one type of option, and another variation is a put option. Call option is a financial contract that gives the option to a buyer, so that a buyer will have a right but not an obligation to buy a stock or bond or commodity at a certain price within a specific time period. So option is a derivative. Derivative is derived from an underlying asset, and here the underlying asset could be a stock. And here it has an example of option contract. So this option gave the holder the right to buy 100 shares of Apple stock at $100. And the expiry date is in 3 months. And on the left-hand side, if you can see my cursor, this is a payoff chart or P&L chart. So to buy this option, it costs a buyer $2. $2 times 100 share, that's $200, right? If 3 months later, Apple stock below $100, then the buyer will have a loss of $200 because the buyer bought an option for nothing. This is a situation called out of money, not making any money. However, if you predict Apple price would go up, and 3 months later, the Apple price right now is at $110. You will make a profit of $800. You will be at here. Can you see my cursor? Yeah. Right. Right. Well, why is $800? Is you have a cost of $2 per share, and if at $110, you have the right to buy the stock at $100. And now the Apple is trading at 110. You will make $10 less $2, which is $8 per share, and in total, you will make $800. Does it make any sense? Okay. So this is a simple derivative. The derivative is different than underlying stock. I know you are learning to do stock picking, and the derivative is derived from underlying asset, and give the holder the right to buy at a certain price. And the reason that people want to use the derivative is you can speculate the market. Say if you predict this Apple stock will go up, and you can use $2 to buy the upside, and later on make a lot of money. And this is a much better leverage than just borrow money to buy the underlying asset. And of course, on the other hand, people also using this optional derivative to do hedging. There is a many scenario that hedging will make sense. Hedging is a way to reduce risk. And for example, if I have a mortgage is a variable rate, and I only have a limited capability to pay down my mortgage, and if I predict the price of the mortgage will go up, and the interest rate will go up, I'd better to lock into a fixed rate of a mortgage. A similar situation also in the commercial domain. To do that, one of the mechanisms is to buy a swap. A swap allows you to transfer from variable rate to fixed rate. That's another type of derivative based on interest rate. The same thing if you depend on your business depend on the oil supply, and you cannot tolerate the fluctuation of a commodity price. Over there, also makes sense to buy a derivative or buy an option or future contract so that you can limit the risk. So hedging also makes sense, and the people do use the derivative for speculation. This is essentially about the size of derivative market, and this is also give you a sense why banks need a lot of compute power, because there are a lot of money at stake. Sure. All those banks dealing with a commodity market is $44 billion for silver, and gold is $10 trillion for gold market. Stock market is around $70 to $90 trillion, and global debt is $252 trillion. But if you look at derivatives is at $1,000 trillion range. The derivative we just talked about, like option option is one type of a derivative. There are many other type of derivatives. The aggregate amount of derivatives is at $1,000 trillion. And for large bank, they may own tens of $1 trillion of derivative asset. And the compute power, one of the usage of the compute power is to do the pricing for those derivatives. Why they can or they want to spend such amount of money for compute is because a lot of money at stake. So far so good. Then let's look at how the option is being calculated by computer. Here, I have to introduce some formula, but you don't have to understand exactly how this partial differential equation works. Maybe you just get a high-level sense how it works. Here, the ST is the current stock price. This is for the call option, for option. And the K is for strike price. Remember, the call option is about give the holder the right to buy certain stock at a certain price. And the value of the right to buy such an option essentially is about the future stock price with some variable minus K, the strike price, with some variable. The E to the power of RT is a discount factor. You need to discount the future money to today. This is the present value. And ST times this variable minus strike. ST times this variable essentially is what you get, right? You have this right? The higher the S to go up, the better for you. And the K is the strike price. The right, the price, the right of the for you to buy this stock. And the K, this is what you pay. The difference is the value of your option. What you want is you want this stock to go as high as possible, and then you pay certain price for the option, and you will maximize the value you have. Of course, when you do the pricing for the option, and this is a formula to calculate the price of the option. And this 2n term essentially the normal normal random variable, and which based on some other terms such as time to maturity and also stock volatilities, right? This is a normal distribution term. So this is a high-level idea for Black-Scholes, and this is one of the most famous formula in financial engineering, and this formula created by these three gentlemen, Fisher Black, Marion Shaw, and Robert Merton, and they got a Nobel Prize for this formula. And this formula also has a number of assumptions. One assumption is this option, the European call option, can only be exercised at expiration, which is different than other type of options. For example, American options, which can be exercised at any time. And also other assumption like market efficient, There are no transaction costs to buy the option, and also risk-free rate and the volatility of the stock underlying are known and constant. In reality, this assumption may not be true. However, this formula gave a very good baseline how to do the pricing for the option. I know this is maybe a little bit mathematics, and also maybe this option is a new concept to you. Are we good so far? Any questions so far? You can raise your hand if you're all good. You have a question?
Yeah, why do we need like a formula to determine the price instead of like a supply and demand of these contracts?
This is a very good question. In the real market, the real price also driven by supply and demand. And just like a stock, if you have more people to buy, and the price will go up. This is an inflow and outflow. However, for any asset you want to own, you always want to know the future payout. For example, if you buy a house, if you buy commodity like oil, if you buy a stock, you always want to know the future payoff, and the payout or cash flow essentially determine the price of the option. And when you have more people to buy, that's indication there's more people believe that the future payout or cash flow will be higher, right? So this is I think maybe the fundamental difference between cryptocurrency and other type of asset. For cryptocurrency, that price almost 100% determined by supply and demand, because there's no underlying, and the cryptocurrency doesn't generate any future cash flow. Cryptocurrency doesn't have underlying like a company, the stock or commodity or the oil or weight or things like that. However, when we're looking at other type of financial product, it also always have underlying. This underlying have intrinsic value, and the pricing will be based on the intrinsic value, the future return. And of course, when you do the real market dynamic, the supply demand will also contribute. But if without a future potential to generate the cash, there will not be any demand. If this is a piece of junk, nobody will want it. And the cryptocurrency is a very special case. Does it make any sense? Okay. Okay. So let's look at other type of options. There are more complex options. This is also the reason why you need computer power, right? And this is another type of option called a knockout European call option. It's also called a barrier option. It's the same as a European call option, except there is one additional term. This one additional term is this one. This is B. B is the barrier. So when you will make money, of course, the stock need to be higher than the strike price. And another condition is during the entire duration of your option, the stock price has to be always below a certain barrier. And if you look at this chart, right? So if it's higher than a barrier, your option was nothing. However, if your option, if your stock is between this range, between the barrier and this range, you will make money. So the reason the people invent this type of option is to want to limit risk and also lower down the option price. If you don't have this barrier, this option price will be much higher than this barrier option, because with this barrier, it limits the upside. You won't make any money if a stock go beyond this barrier. So this is another type, and this type of option, it doesn't work. The previous formula, Black-Scholes formula, doesn't work for this option. And there are some even more exotic type of options. There is one called auto-callable options. There is another one called the target accrual redemption forward. You could have a multiple payout at a different payment date. You could have knockout is barrier, and you could also bundle with other options. So for such a complex options, you will need to use one of the computational techniques called Monte Carlo simulation. You will not have a closed form formula to directly calculate the price, and you will need to use a simulation approach to calculate the future potential cash flow, and then do the average, and then discount back to calculate the price for the derivative. And this is one of the biggest reason you need to have a lot of compute power to understand the true price, true value of your derivative. So what is a Monte Carlo simulation? Monte Carlo simulation is a method estimating the value of unknown quantities using principle of inferential statistics. Essentially, it's just about running a lot of random sample and try out, and later on you do the average to derive the value. Just like flip a coin 1,000 times, you will know that the probability is 50% chance for head, 50% chance for tail. And this is the principle of regression to mean. And by running a lot of such a random paths, and then later on do an average, you will derive, you will approximate the true price. And here, for example, this is running a lot of Monte Carlo simulation paths, and here is the plot for those simulation paths, and you can see the mean. This is for European call option. The mean, I think one is a blue bar. Blue bar is the distribution of Monte Carlo simulation. It's very close to the option price from Black-Scholes formula. So for the vanilla European call option, you have a Black-Scholes formula, but for barrier option, you have to rely on this Monte Carlo simulation approach. In this case, you can see if you have a path, this is a stock price involving if it exceed this barrier, this horizontal line is the barrier, then those passes will not be counted. And essentially it involve and calculate the final price, and we get rid of all the ones exceed the barrier during the evolution, and the remaining ones we do an average and a discount back to today, and that's the value of your option. So you need to do a lot of calculation. Why is that? Let's look at a program. So this is the whole thing of stock price evolution based on assumption of random behavior, random walk behavior. And this is essentially geometric Brownian motion. And this is a definition of geometric Brownian motion. Is a stochastic process to generate a sample path of underlying equity. And this mu is essentially the trend, is expected return with dt, and then this sigma is a volatility term, and this dw again is a normal distribution, and this normal distribution essentially is this Brownian motion term. Right? And if we don't need to worry about the details of this formula, partial differential equation. Look at the complexity of the program. What you need to do for Monte Carlo simulation, you essentially need to have this nested loop. You need to go through all the passes, and for each pass, you go through all the time step. Here is 1 year. That's why it has 365 days. And for every single step, you just use this formula to calculate. This is the drift. Drift is the mu times dt and plus volatility times this Brownian motion term. And this is the change of a price. And once I calculate the price of this point, I can move to the next time point and then do another calculation. And then you add to the previous step. And this is a one possible scenario how your stock price will evolve in the next year. And after that, you just sum everything together and discount back to today. So the complexity is this one. And to make it work, you may need to run 1 million paths. And depending on the duration, there are many days. And sometimes for one point per day is not sufficient. You may need to use multiple points per day. And that will involve more calculation. And this is exactly why this Monte Carlo simulation is very expensive to calculate. Any questions so far? I know I also introduced some additional concept just to help to understand what's the driver, why banks need a lot of computer power. Questions so far? Okay.
Yonggang, are the simulations typically run offline or online?
It depends. There is two parts. One is during the day trading, day trading, you will need to run this simulation to determine the price for the option, for the derivative. Over there, you need to have real time. For example, if a bank is the market maker, want to sell you something, and I need to determine the price first. And if I'm an institution buyer, I need to buy something, I also need to run this to determine the price. I want to make sure what I will buy worth the money. And how to understand the true value is to look at the future potential return based on this type of simulation, and then discount back to determine the current price. If you don't have this information, you essentially just doing trading blindly. Right? So during the daytime, you need to do real time, and during the nighttime, for the risk management, you need to essentially calculate the price for all your instrument and determine what's the ultimate risk and how much money you need to set aside to determine the risk exposure and also do the capital allocation.
Okay, thanks.
So let's look at a little bit more to look at how such Monte Carlo simulation for barrier option, how this calculation can be accelerated through GPU. GPU have this many core architecture, have this SIMD type of instruction, single instruction, multiple thread. And this is perfect for Monte Carlo simulation, because all those Monte Carlo simulation paths actually independent, and it can evolve independently. So a very simple approach to do a simulation on GPU is to run many threads. And here is how you define the GPU, run on GPU. For GPU, you have a grid, right? You have a grid. This is a one grid, 1D block. And you could also have a 1D grid, 2D blocks, 3D blocks. Essentially, each block have many threads, and all those threads can be executed in parallel. And you can define what's the block size for the GPU, and the number of threads essentially is determined by the number of paths divided by block size. So you launch this kernel on GPU, and then on GPU, they will execute thousands or maybe tens of thousands threads in parallel, and each thread will do the evolution for one path. And here exactly just go through the time steps. Go through the time stamps and using the formula we used before. And here it also consider a barrier. Barrier is for the barrier option, right? We only continue to evolve when the current price is bigger than the barrier. Right. So and then after that, and you calculate the payoff, do the average calculated payoff. The GPU will significantly speed up such a calculation. Essentially can give you maybe 500, in this specific case, can give you 500x speed up. And you probably notice this is a C++, and previously it's a Python, and the C++ will also give you maybe 10x compared with the Python. Python can only do based on interpreter and single thread execution. And here we use 10,000 or tens of thousands threads all executed together using C++ and OC running CUDA kernel on GPU, give you significant speed up. And this is actually related to the question Alisa asked before, right? Within the bank won't be just one trade. Actually, the bank have thousands of trade. There is two types of calculation. One is online, determine the option price for the trader, and also calculate the Greeks for trader. And the second type is doing the end of day risk management. This is from 10K or 10Q from 2011, right after financial crisis. You can see this risk process. This risk process called CVA, created value adjustment, have a big impact to the bank's bottom line. And this is still the case. If you look at the 10K, 10Q of those banks, this CVA, this risk management also have a big impact to the bank's bottom line. To calculate this risk for the bank, for the entire bank, you essentially need to have this three dimension, this instrument. One call option is one instrument. You may have millions of such instruments. And you may have many scenarios. Scenarios is about all the different assumption of the market. Interest rate could be, 20 basis point up. Commodity price could be this one. Exchange rate, inflation rate, all those market factor and the scenarios need to accommodate all the combination of the important market factors, and then the time scale. And some of the contract could be very long, could be 5 years, could be 10 years. And when you calculate this cube, you essentially need to conduct trillions of calculation. And scalability is a challenge, and reliability, the agility and the performance, and also you want to make sure all the computational results are doing useful work. The cost is another factor. You don't want to break the bank. So I know we only have 5 minutes, and I'm gonna move a little bit faster. To do the calculation, there's different way. We use a GPU here, right? However, when you have this millions of derivatives, this is a number of scenario. You need to run nested monocolor simulation, and this is for one, right? And when you need to run this complex calculation, you need to run distributed computing. MPI is a tool to do that. However, MPI have pros and cons, have challenges. And then we also invented another paradigm. This is for high performance scatter and gather, provide more of elastic cloud native experience for parallel computing, and support millisecond round trip latency. This is another type, right? It's task driven processing. This is an IBM product. And for such a complex risk analytics application, you may need all the different type of distribution paradigm, scatter, gather, dynamic parallel, with all the data movement consideration and optimization. And recursive is another popular choice. When you calculate counterparty risk, you can have multiple level of parallelization. MapReduce is another one. And you also when you have many risk flow, many jobs, many tasks, millions of jobs, billions of tasks running on hundreds of thousand cores, thousands of GPU. You need to have a proper workload and resource management. That's why there's a queue, there's a priority, there's a preemption, there's SLA based guarantee. You want to have your CPU, GPU, storage network all doing useful things and get your job done according to application SLA. And this is a utilization of the production, right? And this computing grade keep growing for this bank from 1,500 core to tens of thousand core to hundreds of thousand core. The last thing I want to cover is there's a trend going on for AI. This AI is called model free. Model here, we talk about differential equations, the stochastic differential equation type of model, which determine the price of a derivative. And the model free is means we don't need to use that model. We use more of AI approach to determine such a price. I have a couple of examples for that, and I have a reference at the bottom. This is using model to approximate the Monte Carlo simulation, essentially using the AI model to generate the price. And then people also working on hedging. Hedging is about reducing the risk. If you sell a call option, you need to buy certain stock in order to reduce the risk. And if you traditionally you use a delta hedging, however, delta hedging is have a limitation, have assumption. For example, there's no transaction cost, which is not the case. Reinforcement learning is being used here. You can see here, delta hedging is not optimal, and you will need to, if you use a reinforcement learning, it can learn a better policy. For example, in this case, under hedge is better, more optimal, give you more profit compared with delta hedging, if there is a trading cost involved. So there is a paper at the bottom, and this is a paper also from Yonggang Hu. Yonggang Hu wrote this famous book, right? Every trader quants have this book on their desk for financial engineering. And the last thing I want to mention is quantum also on the horizon. Quantum computing have a potential to have impact in the field of machine learning, optimization, and simulation. Specifically, today we talk about simulation for derivative pricing. The quantum could provide a quadratic speed up over Monte Carlo simulation. So what you can see here is today we talk about the parallel computing through HPC. We talk about one specific use case in Monte Carlo simulation, the derivative pricing, and also risk management. We talk about the driver, business driver for simulation and the demand for HPC. And then we also talk about the potential for AI and the future for quantum computing. So I think that will be all for me. I know we are end of hour. I still have time. I can answer more questions if you have more questions. If you want to stay longer to ask more questions.
Thank you very much, Yonggang. Are there any questions? If anybody has questions, please feel free to come off mute.
Okay, go ahead. Yeah.
Also, sorry in advance. I lost my voice 2 nights ago. I'm slowly regaining it.
Yeah.
So
no worries.
I think Eliza had given you a little heads up about like one of our teams that we're working on. So we're using a bunch of hedge fund data to try and determine what would be like good stocks to choose for the future. And we wanted to cross-reference it with a lot of current data right now. So I wanted to know if you had any good input in terms of what styles we should be looking for and like what types of, like we've gone through a few models now, but like just very basic bones, like just for regular stocks, nothing too complicated. What do you think like the best factors are that we should be looking into?
Yeah, I actually I don't know what Alisa already covered. I think there are many things you could consider. The fundamental of the stock, the past historical performance, and also the future trend and some additional alternative data sources you could consider. For example, this Reddit is become very popular, and the GameStop, the AMC, BlackBerry just being treated as like a crazy. The signal from a Reddit board could be a very important signal. Before we're looking at the time series and things like that, but the signal over there could be even more important. You may give it a higher weight to that type of a signal. That will require some natural language processing. I don't know whether you will use some tool like that to look at alternative data source. And then the next thing you will look at is the option, for example, the option market. The option market have give you a very good indication of future potential or trend or people's belief of how the stock will be traded. So this option market is another source of data. The best source of data is if you are insider of the company. You know the company gonna be acquired or whatever, and then you have the best source of data. So that's another consideration. And then when you put multiple stocks together, the most important part will be looking at the correlation of those stocks, and also your strategy to build a portfolio. Because this will not be just an individual stock. You need to look at the beta, looking at the risk of entire portfolio, and what's the goal of your portfolio. Whether you want to maintain risk neutral, want to make it more aggressive, right? Hedge fund use a lot of risk neutral approach. So this portfolio optimization is a very good area to apply the reinforcement learning I was talking about, right? If you guys have interest in this area, maybe we can talk more in future, because reinforcement learning is about a dynamic decision process. It's about optimization, but the optimization is not at one snapshot. And for portfolio optimization, the rebalance of your portfolio is exactly a dynamic decision problem. I gave one example in the talk saying, oh, you have this portfolio of one derivative, and then you need to also own certain underlying. And by using reinforcement learning, it will help to determine how to rebalance the portfolio, how much additional stock to buy in order to cover the risk and to cover the potential either upside or downside of the portfolio. So you ask a big question. If I know how to do it perfectly, I probably won't work for IBM anymore. So it's definitely challenging problems. But from computer science perspective, there are a lot of things you can apply to machine learning, data science. If you have learned PCA, you can throw a few of the data science analytic tool over there to optimize your portfolio. Yeah.
Okay, cool. Great. Thank you so much.
Yeah. Okay. Go ahead.
You mentioned the transition to just letting the deep learning algorithms replace the more formal equations. Is that just sort of you take out one algorithm stopping the other, or is that more significant paradigm shifts either in terms of compute power or?
Your voice is kind of muffled, and right now also kind of broken on my side. I don't know whether other people heard the problem, heard the question. Could you repeat?
I think it's my connection. Is it better now?
Yeah, a little bit better. Yeah.
I just wanted to know a bit more about the transition to learning algorithms instead of more formal equations. Has that changed sort of more significantly the paradigm, whether in terms of compute power or what variables can be taken into account, or it's just a more accurate algorithm that sort of is swapped in?
Maybe it's still my machine, right? I use my laptop speaker. You talk about computer power, and I missed the last part. Yeah.
I think it's my connection. I'll try one more time. But I wanted to know whether the transition to learning algorithms as opposed to formal equations has changed things as a more significant paradigm shift, whether in terms of compute power or what variables are taken into account, or it's just you swap out one algorithm for the other, and it improves some degree of accuracy.
Okay. You talk about the learning algorithm. Why learning algorithm better than other type of algorithm, and is that what you ask?
I was asking more in terms of to what degree has it changed the way things run?
Okay, from compute infrastructure perspective, what things has been changed, right? Okay, this is also a good question. So this before, right? Before, when you look at a lot of data science based techniques, it's all based on linear algebra calculation. Not all, but many of them. I think Lisa have a lot of background on that. He can provide a better answer. So it's a linear algebra based calculation. But if you look at learning is an optimization process. And of course, I have linear algebra involved because this is all about a big matrix multiplication. When you have a language model, this attention model is all about matrix multiplication. But also have optimization process, right? There is a cost function. You compare the label, the data, the y and predict data, and then calculate the difference, and then to do the gradient descent to update your function. So from computing perspective, it's an iterative approach, and you need to run a lot of such iteration so that enable such a gradient design. And there are a couple of things we need to consider. One is data ingest. data ingest. Well, if you want to make this gradient descent to run faster, you will need to run multiple such things in parallel, and each update will have 1 mini batch, and that will require parallel data ingest to ingest a different set of data. And then another one is when you have a parallel component to do such an update, you also need to leverage a process called all-reduce. All-reduce essentially, you may have multiple learner running in parallel, and each learner will look at a certain part of data and then determine the difference, and then determine the gradient, how you want to update the model. But you cannot just work on your own set of gradient and weight. You have to synchronize with all the others, and that will require gradient synchronization. This is all-reduce process. And this all-reduce process, depending on the size of a model, could be also very intensive, require very strong network to do it very efficiently. Think about if you have 100 billion parameters, and the size of a parameters are very big. And if you want to synchronize and send the gradient or weight of those parameters, require a very big network, have a very big network demand and bandwidth. Over there's multiple strategy. There's a data parallel, there's model parallel, within model parallel, there's a pipeline parallel, there's called a tensor parallel, right? So from a computing infrastructure perspective, you need to look at parallelization within the node, within the GPU, and also parallelization cross node, and the data ingest part, and also the all-reduce and the data communication for to carry out this learning process. So there's high demand for all the different computational technique for AI for training. In many aspects, AI was enabled because of the advancement in computer science and computer technology. Jeffrey Hinton, one of the godfathers for AI, has been working on neural network, deep neural network for many, many years. In 1980, 1990, 2000, but until they have a very strong compute power, they didn't make a lot of progress until the availability of HPC like compute power.
Okay, I think we'll thank Yonggang because we're 15 minutes over time. Thank you so much. This was extremely interesting and informative.
Yeah, thank you. Thank you for having me. Thank you for this opportunity. And all the questions, fantastic question. Thank you all.